This video is a guide for calculating pi factors. It also sums up the things I told you in my last video. You can find this guide on my website. From there you can download it or save it on your computer. The link can be found in the description of this video. The first thing you have to do when you want to calculate pi factors is to think about all the quantities your mathematical or physical problem could depend on. We call these quantities Q1 to Qn. In our example, where we wanted to find a formula for the cycle duration t of a mathematical pendulum, these quantities Q1 to Qn could be small t, small m, small l, and small g, where t describes the cycle duration, m describes a mass, l a length, and g is a constant, the gravitational constant. The second step is to find out the dimension of the quantities Q1 to Qn. If you do not know the dimension of one of these quantities, you can use the internet to find it out. The third step is to write the quantities Q1 to Qn together with the basic dimensions their dimensions depend on in a table like that. So here we have the quantities Q1 to Qn, and here on the left side we have all the basic dimensions, the dimensions of the quantities Q1 to Qn depend on. So for example, these basic dimensions could be the time capital T, the mass capital M, the length capital L, and so on. When we take a look at our pendulum example, where we wanted to calculate the cycle duration t of a mathematical pendulum, this could look like this here. So here we have the important quantities t, m, l, and g, and these are the basic dimensions these quantities depend on. So time, mass, and length. That's it. In the fourth step, we take a closer look at the dimensions of Q1 to Qn. The dimension of these quantities will be some product of the aforementioned basic dimensions. Each of these basic dimensions will have an exponent that tells you how often this basic dimension appears in the dimension of the quantity. Now we fill in these exponents in the table accordingly. What we get is a matrix A with columns C1 to Cn. I think this is easier to explain when we look at our pendulum example. Here we have the dimensions of the quantities T, M, L, and G. Now we take a look at these exponents here. 1, 1, 1, 1, and -2. They tell us how often a basic dimension appears in the dimension of a quantity. Now we just have to fill these exponents here in the table accordingly. So when we take a look at small t, we know it only depends on capital T, and this to the power of 1. So we have 1 time t. It doesn't depend on mass, so 0, and it doesn't depend on a length, so also 0. When we take a look at small m, the dimension of small n is capital M to the power of 1, so we have 1 time mass, 0 time and 0 length. The same thing with small l. And when we take a look at small g, it depends on l to the power of 1 and t to the power of -2. So -2 for t, but no mass, so 0, and 1 time length. In the fifth step, you have to calculate the rank of the matrix A. We call this rank K, and then you have to choose K linear independent columns of A. We will also assume that the first K columns of A are linear independent and pick them. If this is not the case, we can simply switch columns so that it is the case. So here we see how we pick K linear independent columns of the matrix A. And we assume that the first K columns are linear independent because we can always switch columns. So that this here is the case. Please also note that there is often more than one option to choose K linear independent columns. Your choice here will affect the pi factors you get later. When we take a look at the pendulum example, we can, for example, choose the first 3 columns of this matrix here, because these columns are obviously linear independent and the rank of the matrix is 3. So this is a possible choice for step 5. In step 6, you have to write the remaining columns ck plus 1 to cn as a linear combination of the columns you picked earlier. So of these columns here, c1 to ck, which are linear independent. So when writing this down, this has to look like this here. So the columns ck plus 1 to cn are written as a linear combination of these columns here. Maybe this is a little bit easier when we take a look at the example. So in this example here we picked the first 3 columns, and this here is the only remaining column, so -2, 0 and 1. So this means we have to write this column here as a linear combination of the first 3 columns. So this is pretty easy and has to look like this here. So here we have written the last column here as a linear combination of the first 3 columns. We are interested in these values here, a, I, j. So in our example, -2, 0 and 1, because we will need these values in the next step. So in step 7, we can write down the n-k dimensionless pi factors. They can be calculated by using this formula here. So here we have the quantity that corresponds to one of the remaining columns. So here, or in our example, this column here. And then we have a product of some other quantities, and these quantities are the quantities that correspond to the columns we picked earlier. So these columns, the first k columns. So we always have a quantity that corresponds to one of the remaining columns, and then a product of the picked quantities. And we also have to raise these quantities to a particular power, and these powers are minus AIJ. So these values here we calculated in the sixth step. So in our example, in our pendulum example, we only have one pi factor. So we have to pick the quantity that corresponds to the remaining column, so G. Then we add the picked quantities, so TML, this here. And then we have to raise these quantities to the power of these values here. And we also have to change the sign in this process. So minus 2 becomes 2, 0, 0, and 1 becomes minus 1. So we have these values here. Now we can use the pi factors to achieve something. For example, you can use the pi theorem to derive a physical formula. Or you can use the pi factors to scale a differential equation. If you want to derive a physical formula, you need to know the pi theorem at first. The pi theorem states that if pi1 to pi n minus k are all the pi factors you calculated earlier, then one of the pi factors, for example pi1, can be written as some function r of the other factors. A special case is when n minus k is equal to 1, which means that there is only one pi factor pi1. Then pi1 is equal to c, where c is some constant.